Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Arthur Cayley stands as a pivotal figure in the development of modern mathematics, his contributions forming the very bedrock upon which much of contemporary algebraic structure rests. We begin our exploration not with a chronological account of his life, but with a central problem that shaped his early career, the quest for invariance amidst transformation. The 19th century witnessed a flourishing of algebraic geometry, a field grappling with the challenge of classifying geometric forms, conic sections, quadratic surfaces, and beyond, in a manner independent of their specific orientation or the chosen coordinate system. This pursuit led directly to the development of invariant theory, a field where Cayley, alongside his lifelong collaborator, James Joseph Sylvester, played an absolutely dominant role. The core problem was to identify those properties of algebraic forms, specifically polynomials, that remained unaltered under linear transformations of the variables. Consider a simple conic section described by a polynomial equation in x and y. Rotating or scaling the coordinate axis changes the coefficients of the polynomial, yet the underlying geometric object, the ellipse, parabola, or hyperbola, persists. Invariant theory sought to capture this essence, to mathematically isolate these unchanging characteristics. Cayley's approach was profoundly innovative. He developed a systematic calculus, a symbolic machinery for generating invariants and covariants. Invariants are functions solely of the coefficients of the polynomial, remaining constant under linear transformations. Covariants, conversely, are functions of both coefficients and variables, transforming in a predictable manner under these transformations. This was a monumental undertaking, a computational tour de force demanding the creation of entirely new symbolic techniques. Cayley's work, culminating in his extensive memoirs upon quantics beginning in 1854, meticulously details this intricate process. These memoirs are not merely collections of results, but a systematic exposition of a new mathematical language, a language designed to express and explore the deep structures underlying algebraic forms. The binary quadratic form, a polynomial of degree 4 in 2 variables, provides a particularly illustrative example. Cayley calculated its two principal invariants, conventionally denoted S and T. These invariants are not merely arbitrary quantities. They are fundamental characteristics of the binary quadratic, providing a means to classify and distinguish different forms. The values of S and T, for instance, determine whether the quadratic represents 4 distinct real roots, 2 distinct real roots, and 2 complex conjugate roots, or other such configurations. This precise classification, enabled by Cayley's invariant calculations, demonstrates the power and depth of his methods. Cayley's work did not emerge in a vacuum. His symbolic methods drew heavily upon the work of George Boole, whose investigations into symbolic logic and the manipulation of differential operators provided a fertile conceptual ground. Boole's emphasis on the abstract manipulation of symbols, independent of their immediate interpretation, profoundly resonated with Cayley's approach to invariant theory. Furthermore, the earlier work of Lagrange and Gauss on transformations provided a crucial foundation for understanding the very nature of the problem Cayley sought to solve. The contributions laid the groundwork for Cayley's sophisticated symbolic calculus. The influence of Cayley's work on invariant theory extended far beyond the immediate impact of his specific calculations. The sheer computational complexity of the Cayley-Sylvester approach, their constructive method of generating invariants, presented a significant challenge. This difficulty directly motivated David Hilbert's landmark 1820 proof of the basis theorem. Hilbert's proof, a profound achievement in its own right, demonstrated, using a non-constructive, existential argument, that a finite set of invariants could generate all invariants for a given form. This result revolutionized invariant theory, providing a powerful theoretical framework that transcended the limitations of the computationally intensive methods pioneered by Cayley and Sylvester. Hilbert's work, while fundamentally altering the direction of the field, stands as a direct testament to the profound impact of Cayley's earlier contributions. The challenge posed by Cayley's constructive approach ultimately spurred a major shift in the field's methodology. It was a challenge that led to a deeper, more abstract understanding of the underlying mathematical structures. Hilbert's achievement, therefore, is inseparable from Cayley's initial work. It is a direct consequence of the problems and methods Cayley first brought to the forefront. Cayley's exploration of invariants, far from being an isolated pursuit, provided the fertile ground for his subsequent contributions to matrix algebra. His work in invariant theory, with its emphasis on linear transformations, naturally demanded a more efficient and concise way to represent and manipulate these transformations. This inherent demand for more streamlined symbolic language, formed the very impetus for his next major contribution. The intricate calculations involved in invariant theory required a more powerful mathematical tool, a tool that would ultimately transform the landscape of algebra itself. This brings us to the next stage in our exploration of Cayley's legacy. The intricate calculations involved in invariant theory required a more powerful mathematical tool, a tool that would ultimately transform the landscape of algebra itself. This brings us to the next stage in our exploration of Cayley's legacy, his creation of matrix algebra. Linear transformations, the very lifeblood of invariant theory, were previously treated as cumbersome arrays of coefficients. Mathematicians grappled with systems of linear equations, manipulating them through ad hoc methods, lacking a unified symbolic language to represent and operate on entire transformations as single entities. Imagine attempting to conduct orchestral music by describing each instrument's part individually, rather than using a conductor's score. Cayley provided the score, the formal system that brought order and elegance to these mathematical operations. His seminal 1858 paper, A Memoir on the Theory of Matrices, marked a watershed moment. In it, Cayley boldly defined a matrix as a single, self-contained algebraic object. This was a profound conceptual leap. He then systematically laid the foundations for a complete algebra of matrices, defining operations that seem almost self-evident today, yet were revolutionary at the time. He established the rules for matrix addition, scalar multiplication, and, crucially, matrix multiplication. Matrix multiplication, as Cayley immediately recognized, possessed a peculiar property that distinguished it from the algebra of ordinary numbers. It is non-commutative. That is, for two matrices A and B, the product of A multiplied by B is generally different from the product of B multiplied by A. This departure from the familiar commutative law was a pivotal insight. demonstrating that matrix algebra was a distinct mathematical system with its own unique rules. This revelation built directly upon William Rowan Hamilton's earlier exploration into quaternions. Hamilton's 1843 discovery of these non-commutative entities served as a crucial precedent, demonstrating that a consistent and useful algebra could indeed exist separate from the commutative laws governing real and complex numbers. Cayley, undoubtedly familiar with Hamilton's work, extended this concept, creating a more general and practical algebra. Cayley did not stop there. He further defined the identity matrix, the matrix equivalent of the number 1, which leaves any matrix unchanged upon multiplication. He also defined the matrix inverse, the equivalent of a reciprocal, which when multiplied by the original matrix yields the identity matrix. These definitions completed the basic framework of matrix algebra, providing mathematicians with a comprehensive toolkit for manipulating linear transformations. A particularly striking example of the power of Cayley's matrix algebra is embodied in the Cayley-Hamilton theorem. This theorem states that every square matrix satisfies its own characteristic equation. The characteristic equation is a polynomial equation derived directly from the matrix's determinant. To illustrate, consider a 2x2 matrix. The characteristic equation will be a quadratic equation. The Cayley-Hamilton theorem asserts that if you substitute the matrix itself into this equation, replacing the variable, the result will always be the zero matrix. This theorem establishes a profound link between a matrix and its algebraic invariance, a connection that directly echoes Cayley's earlier work on invariant theory. It demonstrates that a matrix is not merely a collection of numbers, but an object with inherent algebraic properties that can be expressed in terms of polynomial equations. The Cayley-Hamilton theorem has become a cornerstone of linear algebra, a testament to the depth and elegance of Cayley's initial formulation. The impact of Cayley's matrix algebra on modern science and technology is immense. Virtually ubiquitous, it forms the very bedrock of numerous fields, providing the essential mathematical language for describing and manipulating linear transformations. Consider quantum mechanics. In 1925, Werner Heisenberg, grappling with the perplexing nature of quantum phenomena, recognized the non-commutative structure he needed for his revolutionary new theory was precisely encapsulated in Cayley's matrix algebra. Heisenberg's matrix mechanics, one of the two original formulations of quantum mechanics, relies entirely on representing physical quantities as matrices and using matrix algebra to predict their behavior. The non-commutativity of matrix multiplication directly reflects the uncertainty principle, a cornerstone of quantum theory. Beyond physics, matrix algebra is indispensable in computer graphics. The transformations used to render three-dimensional objects on a two-dimensional screen, rotations, scaling, and translations, are all represented by matrices. The successive application of these transformations is achieved through matrix multiplication, allowing for complex visual scenes to be generated efficiently. Without matrix algebra, modern computer graphics would be virtually impossible. Data science provides yet another powerful illustration of the relevance of matrix algebra. Techniques such as principal component analysis, PCA, rely heavily on matrix decomposition to reduce the dimensionality of data sets, identify underlying patterns, and extract meaningful insights. PCA uses eigenvectors and eigenvalues, concepts deeply rooted in matrix algebra, to find the principal components that capture the most variance in the data. Even network theory, the study of interconnected systems such as social networks or the internet, relies on matrix algebra. Adjacency matrices, which represent the connections between nodes in a network, are analyzed using matrix methods to determine network properties such as centrality, connectivity, and community structure. The development of matrix algebra did not occur in a vacuum. Cayley's work was influenced by several key figures. As previously mentioned, William Rowan Hamilton's discovery of quaternions provided the crucial precedent for non-commutative algebra. Cauchy and Jacobi's extensive work on determinants laid the groundwork for understanding the properties of matrices and their characteristic equations. Cayley synthesized these ideas, creating a coherent and powerful algebraic system. Cayley's influence on subsequent mathematicians is equally profound. Peter Guthrie Tait, a Scottish physicist, quickly recognized the applicability of matrix methods to physical problems. However, the most significant influence was undoubtedly on Werner Heisenberg. As noted, Heisenberg's adoption of matrix algebra for quantum mechanics cemented its place as an essential tool for theoretical physicists. Beyond these specific examples, Cayley's work laid the foundation for the entire field of linear algebra as is known today. Countless mathematicians have built upon his ideas, extending and generalizing matrix algebra in various directions. In essence, Cayley transformed linear transformations from cumbersome arrays of numbers into elegant, manipulable objects. He provided mathematicians and scientists with a powerful language for describing and analyzing linear systems, a language that continues to be essential in a vast range of fields. Matrix algebra stands as a testament to Cayley's remarkable ability to abstract from the concrete, to discern underlying mathematical structures, and to create tools of enduring power and utility. His work in invariant theory provided the problem, the need. Matrix algebra was his brilliant solution. Cayley transformed linear transformations from cumbersome arrays of numbers into elegant, manipulable objects. He provided mathematicians and scientists with a powerful language for describing and analyzing linear systems, a language that continues to be essential in a vast range of fields. Matrix algebra stands as a testament to Cayley's remarkable ability to abstract from the concrete, to discern underlying mathematical structures, and to create tools of enduring power and utility. His work in invariant theory provided the problem, the need. Matrix algebra was his brilliant solution. Beyond the landscape of linear algebra, Cayley embarked on a journey of abstraction that would fundamentally reshape the very foundations of algebra itself. This involved the concept of a group, an idea that had been gestating within specific mathematical contexts yet lacked a unifying definition. The challenge lay in extracting the essential essence of these systems into a formal, axiomatic structure. Prior to Cayley, the idea of a group remained tethered to particular applications. Joseph Louis Lagrange's investigations into the solutions of polynomial equations hinted at group-like structures in permutation of routes, and Évariste Galois's groundbreaking work explicitly employed groups to determine the solvability of these equations. However, these were always groups of something, groups acting on specific objects. The overarching structure remained implicit. In 1854, Cayley published a seminal paper on the theory of groups. groups as depending on the symbolic equation theta to the n equals 1. This work presented the first abstract definition of a finite group. Cayley envisioned a group as a set of symbols governed by a single associative binary operation. The result of combining any two elements within the set according to this operation must also be an element within the set. This seemingly simple requirement, along with the existence of an identity element and inverses for each element, encapsulates the essence of group structure. Cayley also introduced a method for visualizing finite groups through what are now known as Cayley tables. These tables, which he simply referred to as group tables, provide a complete record of how elements combine under the group's operation. Each row and each column is labeled by group element, and the entry at the intersection of a row and column indicates the result of combining the corresponding elements. While seemingly straightforward, this tabular representation provided a powerful tool for analyzing the structure of finite groups and identifying their properties. The cornerstone of Cayley's contribution is Cayley's theorem. This theorem asserts that every finite group G is isomorphic to a subgroup of a symmetric group. A symmetric group is a group consisting of permutations of a set, with a group operation being composition of permutations. The theorem implies that any abstractly defined finite group can be realized as a group of permutations. This demonstrated that Cayley's abstract definition was not a mere formalization, but rather captured the fundamental nature of group theory's concrete origins. It forged a link between the abstract and the concrete, demonstrating that the abstract definition was both powerful and deeply connected to the existing body of mathematical knowledge. The genesis of Cayley's group theory can be traced to the work of Augustin Louis Cauchy on permutation groups. Cauchy's systematic study of permutations, their cycles, and their properties provided a rich source of examples and techniques. Furthermore, Évariste Galois's innovative use of groups to analyze the solubility of polynomial equations served as a direct inspiration. Galois demonstrated how the structure of a group associated with a polynomial reveals whether its roots can be expressed using radicals. Cayley's genius lay in recognizing the common thread running through these seemingly disparate applications and in extracting the underlying abstract structure. Cayley's abstract definition of a group had a profound impact on the development of algebra, while the von Dyck refined Cayley's initial formulation, ultimately providing the modern definition of a group in terms of generators and relations. This approach focuses on describing a group by specifying a minimal set of elements, generators, and a set of equations, relations that dictate how these generators combine. This provides a concise and powerful way to define and study groups, particularly infinite groups. Furthermore, Cayley's work laid the foundation for the field of abstract algebra. This field, championed by figures like Heinrich Weber and Emmy Noether, embraces the axiomatic method to study algebraic structures such as rings, fields, and modules. Abstract algebra has become an indispensable tool in mathematics, providing a unifying framework for studying diverse mathematical objects and their relationships. The modern relevance of group theory extends far beyond the confines of pure mathematics. It serves as the mathematical language of symmetry, a concept that permeates many areas of science. In physics, the standard model of particle physics is built upon Lie groups, continuous groups of symmetries, such as S-3. These groups dictate the fundamental forces in particles that govern the universe. The properties of elementary particles, such as their charge and spin, are directly related to the representations of these groups. Chemistry also utilizes group theory extensively. Molecular symmetries, described by point groups, determine a molecule's physical and chemical properties, including its spectroscopic behavior. By classifying a molecule's symmetry, chemists can predict which vibrational modes will be active in infrared or Raman spectroscopy, providing valuable information about the molecule's structure and bonding. Even modern cryptography relies on group theory. Elliptic curve cryptography, a widely used method for secure communication, utilizes the algebraic structure of elliptic curves over finite fields. The difficulty of solving the elliptic curve discrete logarithm problem provides the security for this cryptographic system. The very act of sending a secure message across the internet relies on the principles that Cayley helped to establish. The journey from concrete examples of permutations to the abstract definition of a group represents a pivotal moment in the history of mathematics. Cayley's ability to discern the underlying structure amidst a sea of specific applications exemplifies the power of abstraction. His work not only provided a unifying framework for existing mathematical knowledge, but also paved the way for the development of entirely new fields of mathematical inquiry. The echoes of Cayley's abstract group theory resonate throughout modern science, a testament to the enduring power of his insights. The power of abstraction that Cayley brought to bear on group theory found further expression in his groundbreaking work on geometry, specifically his development of n-dimensional geometry and his innovative unification of metric geometries within a projective framework. He grappled with fundamental questions: how could one rigorously define and operate within a geometry of more than 3 dimensions, liberating it from the constraints of physical intuition, and how could the seemingly disparate Euclidean, hyperbolic, and elliptic geometries be brought together into a single, coherent system? Cayley's approach to n-dimensional space was resolutely analytical. He defined a point as simply an n-tuple of coordinates, dispensing with reliance on spatial visualization. Geometric concepts, such as distance and angle, were defined by generalizing their algebraic formulas from the familiar 2 and 3 dimensions. This seemingly simple yet profound step allowed mathematicians to explore spaces of arbitrary dimension with the same rigor and precision previously reserved for more tangible geometries. Prior work by mathematicians such as Hermann Grassmann, who developed a general theory of vector spaces, certainly informed Cayley's approach. Grassmann's *bilineal Ausdehnungsslehre*, though initially overlooked, provided a conceptual framework for dealing with higher dimensional spaces algebraically. The influence of René Descartes, who demonstrated the power of coordinate geometry in 2 and 3 dimensions, is also evident in Cayley's analytical approach. The influence of Cayley's work on n-dimensional geometry can be seen in the later development of tensor analysis by Gregorio Ricci-Carbastro and Tullio Levi-Severe. Their work, building upon Cayley's algebraic foundation, provided the mathematical language for Einstein's theory of general relativity, where spacetime is treated as a 4-dimensional manifold. The concept of n-dimensional vector spaces is now foundational to all of modern physics, from the 4-dimensional spacetime of relativity to the infinite-dimensional Hilbert spaces of quantum mechanics. Data science, too, relies heavily on the analysis of data points in high-dimensional feature spaces, a direct application of Cayley's abstract geometric vision. The ability to work with spaces beyond our direct sensory experience is now an indispensable tool in a wide range of scientific and technological fields. Cayley's most striking achievement in geometry was his unification of metric geometries within a projective framework in his sixth memoir upon quantics. Published in 1859, he demonstrated how metric properties could be defined within projective geometry. He introduced the concept of a fixed conic or quadric called the absolute. The distance between 2 points, according to Cayley, could then be understood as a function of their relationship to this absolute. This distance is now known as the Cayley-Klein metric. Jean-Victor Poncelet's development of projective geometry laid essential groundwork for Cayley's approach. Poncelet's asterisk traité des propriétés projectives des figures asterisk emphasized properties of geometric figures that remain unchanged under projection, freeing geometry from dependence on measurement. Julius Plücker's work on line geometry, which treated lines as fundamental geometric objects, also influenced Cayley's thinking by shifting the focus from points to more abstract entities. The specific choice of the absolute, Cayley showed, determine the nature of the geometry. If the absolute is a degenerate conic at infinity, the resulting geometry is Euclidean. If it is a real, non-degenerate conic, the geometry is hyperbolic. This was a revolutionary insight. Euclidean and non-Euclidean geometries were revealed as not separate, mutually exclusive worlds, but rather as different perspectives within a single, overarching projective space. Bernard Riemann's 1854 lecture on the hypotheses on which geometry is based provided a differential geometric perspective that complemented Cayley's algebraic approach. Riemann's concept of manifolds, spaces that locally resemble Euclidean space but may have a different global structure, offered a new way to think about geometry, one that was both more general and more flexible than traditional approaches. Cayley's work directly inspired Felix Klein's 1872 Erlangen program. Klein proposed that a geometry is defined by a space and a group of transformations that leave its properties invariant. This was a direct synthesis of Cayley's work on groups and geometry. Klein's program provided a powerful framework for classifying and understanding different geometries, solidifying Cayley's legacy as a visionary in the field. For instance, Euclidean geometry, in Klein's view, is the study of properties invariant under the group of Euclidean motions, translations, rotations, and reflections. Hyperbolic geometry, similarly, is the study of properties invariant under the group of hyperbolic motions. By defining geometries in terms of their invariance groups, Klein provided a unifying perspective that encompassed both Euclidean and non-Euclidean geometries, fulfilling Cayley's vision. The Erlangen program profoundly shaped the development of geometry in the late 19th and early 20th centuries. It provided a clear and concise way to define and classify different geometries, and it helped to establish the close relationship between geometry and group theory. The impact of Cayley's geometric insights extends far beyond pure mathematics. His work on n-dimensional spaces and projective geometry laid the foundation for many of the mathematical tools used in modern physics and computer science. The ability to think abstractly about geometric structures, independent of physical intuition, has proven to be essential for understanding the complex and often counterintuitive phenomena of the modern world. The unification of different geometries within a single framework has provided a powerful tool for exploring the relationships between seemingly disparate areas of mathematics and physics. Cayley's influence extends to the very way mathematicians think about space. Prior to Cayley, geometry was largely confined to the realm of physical intuition. Cayley's work liberated geometry from these constraints, allowing mathematicians to explore spaces of arbitrary dimension and curvature. This abstract approach to geometry has proven to be remarkably fruitful, leading to many new discoveries and applications. His legacy is not merely a collection of geometric theorems, but a fundamentally new way of thinking about space itself. Cayley also left an indelible mark on the field of combinatorics, particularly in the enumeration of trees. A fundamental problem within this domain concerns the determination of distinct structural arrangements for a given set of elements. Specifically, how many different labeled trees can be constructed using n vertices? This question, seemingly abstract, held tangible relevance in fields such as chemistry, where it played a role in enumerating isomers of saturated hydrocarbons. Cayley provided a definitive answer with his formula, published in 1889. Cayley's formula elegantly states that the number of spanning trees within a complete graph featuring n labeled vertices is precisely n raised to the power of n-2. This deceptively simple expression unlocked a new vista in graph theory, providing a cornerstone for subsequent investigations. Arthur Cayley's work on matrices and determinants influenced Cayley's approach to this problem, providing him with the tools to represent and manipulate the relationships between vertices and edges in a graph. Ronald Reed directly expanded upon Cayley's work, developing algorithms for generating and analyzing these trees, thereby extending the practical applications of Cayley's initial formula. Beyond his contributions to geometry and combinatorics, Cayley ventured into the uncharted territories of algebra, exploring structures beyond the familiar realms of real and complex numbers. Following Hamilton's groundbreaking work on quaternions, Cayley sought to generalize complex numbers further, resulting in his seminal 1845 paper on octonions, sometimes referred to as Cayley numbers. These octonions constitute an eight-dimensional, non-associative normed division algebra. The significance of this discovery lies in its demonstration of the existence of algebraic structures far exceeding the constraints of conventional arithmetic. While multiplication of quaternions remains non-commutative, meaning the order of multiplication matters, octonion multiplication takes a more radical step, surrendering associativity. This means that, in general, for octonions A, B, and C, the product of a times B times C does not necessarily equal a times the product of B times C. This loss of a fundamental property initially relegated octonions to the periphery of mathematical interest. Hamilton's quaternions served as a direct inspiration for Cayley's exploration of hypercomplex numbers. Hamilton's struggle to extend complex numbers to 3 dimensions, ultimately requiring 4, paved the way for Cayley's consideration of even higher dimensional algebras. While initially viewed as a mathematical curiosity with limited practical use, octonions have experienced a resurgence of interest in modern theoretical physics, particularly within the frameworks of string theory, M-theory, and supersymmetry. Physicists such as Murray Gell-Mann had explored the potential role of octonions in describing the fundamental symmetries of the universe. Cayley's formula continues to be a classic result in graph theory, a discipline now pivotal to computer science and network analysis. Algorithms for network routing, data analysis, and social network modeling all rely on the principles that Cayley helped to establish. The octonions, once deemed a mere mathematical abstraction, have found speculative applications in modern theoretical physics, particularly in string theory, M-theory, and supersymmetry areas seeking to unify all fundamental forces of nature. Cayley's intellectual contributions extend far beyond specific theorems or isolated mathematical results. His profound influence lies in a paradigm shift, a fundamental reorientation of mathematical focus towards structure as the central object of inquiry. While many of his contemporaries grappled with solving specific, often applied, problems, Cayley forged the very languages, matrices, abstract groups, and dimensional vector spaces that enabled mathematics to transcend mere calculation and delve into the study of abstract systems and their intricate relationships. He provided mathematics with a new vocabulary, a new grammar for expressing relationships between mathematical objects. His impact is not merely a collection of solved problems, but the creation of a new way of thinking about mathematics itself. Cayley's legacy resides in the establishment of mathematical abstraction as a legitimate and powerful tool. He championed the idea that mathematics is not simply about numbers or geometric shapes, but about the underlying structures that connect these objects. This emphasis on structure has had a profound impact on all areas of mathematics, leading to the development of new fields such as topology, category theory, and homological algebra. These fields, which focus on the abstract properties of mathematical structures, have provided new insights into the nature of mathematics itself. He revealed unity and invariance, algebra and transformation, and geometry in any number of dimensions. Cayley was the definitive architect of mathematical abstraction. He provided the blueprints for a new kind of mathematics, one that is characterized by its generality, its rigor, and its focus on underlying structures. His work has inspired generations of mathematicians to explore the abstract world of mathematics, leading to countless new discoveries and applications. His influence continues to be felt today as mathematicians grapple with increasingly complex and abstract problems. Cayley's legacy is secure as one of the most important figures in the history of mathematics.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.